Hello everyone, my name is Meenakshi and I am a student of BSc Chemistry Honors final year. Today I am going to making a video on physical properties and molecular structure for visually impaired students. Introduction. The various methods used for the study of molecular structure may be broadly classified into following two types. First, method based upon the study of physical properties of the substances such as molar refraction paracore based upon surface tension. Third, optical activity, dipole moment, magnetic susceptibility. Spectroscopic methods such as rotational and vibrational spectroscopy, microwave and infrared spectroscopy, electronic spectroscopy, Raman spectroscopy, nuclear magnetic resonance NMR spectroscopy. The study of molecular structure on the basis of physical properties is based upon the fact that the physical properties listed above are additive as well as constitutive. An additive property of a molecule is defined as that property the total value of which is the sum of values of all its constituent atoms. A constitutive property of a molecule is defined as the property which depends upon the constitution of a molecule, that is, arrangement of atoms within the molecule and the presence of multiple bond rings in the molecule. Spectroscopic methods have already been discussed in chapter 3. Now in this chapter we shall take up a brief discussion on three important physical properties, namely optical activity, dipole moment and magnetic susceptibility, one by one. Let's start. Optical activity. Definition. Plane polarized light. If a ray light travel in any direction, it has vibrations in all directions at right angles to the path of propagation. If this light is passed through Nicol prism, then the Nicol prism devised by scientist Nicol consists of two prisms joined together as shown in figure 5.1. Prism is used. It is found that two beams of light come out, each of which is plane polarized, and the planes of the reflection and the planes of the two are at right angles to each other. By combining with second prism, one of beams undergoes total internal reflection TIR and only one plane polarized beam come out. Instead of nickel prism, a polaroid is also sometimes used. It consists of a film of cellulose acetate mounted between two glass plates, which emerged out of the prism is found to have vibration only in one plane. The light is called plane polarized Nicol prism, thus used as a polarizer. Optical activity. If the plane polarized light is passed through a plate of quartz or turpentine oil of the solution of sugar taken in glass tube, it is found that the light that comes out the plane of the polarized light gets rotated. The substances like quartz, sugar, etc., which rotate the plane polarized light are called optically active substances, and the property of substance to rotate the plane of polarized light is called optical activity. The substance which rotate the plane of the polarized light to the right are called dextrorotatory. Latin dexter means right, and those which rotate the plane of polarized light to left are called levorotatory. Latin levo means left. The method of observing the rotation of the plane of the polarized light is based upon the following principle. If the plane polarized light is passed through another Nicol prism which have its axis parallel to the first of Nicol prism, the light passes through and brightness is observed through eyepiece. On the other hand, if the second Nicol prism is placed with its axis at right angles to that of the first prism called crossed position, the light of the it's completely cut off and the field of view in the eyepiece is dark. At the other position, the brightness is light, but there may not be complete darkness. It is observed that if the two Nicol prisms are set to the cross position so that the field of view is completely dark and the optically active substance is placed between two prisms, the field of view becomes somewhat bright. The second prism has to be rotated through a certain angle about the line of propagation of light to complete darkness again. This clearly shows after passing through the optically active substance, the plane polarized light has been rotated. The degree of rotation depends upon the rotation required to be given to the second Nicol prism to get the darkness again. Thus, just as the first prism polarizes the light and is called polarizer, the second prism analyzes the light and is called analyzer. Specific rotation. The angle in degrees through which the plane of polarized light is rotated on passing through the solution of an optically active substance depend upon the following factors: nature of the optically active substance, concentration of the solution in gram per ml, length of the solution, that is the length of the tube through which the light passes, decimeters, wavelength of light used, temperature of the solution. Thus, if m grams of substance are dissolved in V volume of solution, so that the concentration of the solution in m by V gram per ml, L is the length of tube in decimeter, and alpha is the angle of rotation in degrees, then the found that alpha is directly proportional to concentration in gram per ml into length of the tube in decimeter. Alpha is directly proportional to m by b v into L. Alpha is equal to alpha alpha to t m into L by v, where alpha lambda t is a constant characteristics of the nature of the substance and depend upon the wavelength lambda of light used and the temperature of the solution T degree Celsius. If D line of the sodium vapor lamp is light used and the temperature of the solution is 25 degrees Celsius, then it is written as alpha D25. This constant is called specific rotation of the substance. Thus from the above equation, alpha T lambda V into lambda upon L into M. Now if M is equal to 1 gram, V is equal to 1 ml and L is equal to 1 decimeter, then alpha lambda T is equal to alpha. Hence, specific rotation of a substance may be defined as the angle of rotation produced when 1 gram of the substance is dissolved in 1 ml of the solution. Concentration of the solution is 1 gram per ml and the length of the solution through which light is passed is 1 decimeter. In all the reported values of alpha lambda T, and the concentration of the solution is taken in gram per 100 ml of the solution. It's the C grams of the dissolved in 100 ml of the solution, then we may put M is equals to C, V is equals to 100. This gives from equation second. Alpha lambda T is equal to 100 into alpha upon L into C for solutions. Further, instead of solution substance taken is pure liquid or a solid, then M upon V is replaced by density D of pure substance. This gives alpha lambda T alpha upon L into D for impure liquids or solids. In case of pure solid, L is taken as the thickness of the solid in decimeter. Fourth, molar rotation. The molar rotation is obtained by multiplying the specific rotation with the molecular weight m of the substance and dividing the result by 100 to reduce the magnitude of the number. It is usually represented as m lambda T. Thus, m lambda T is equals to m alpha lambda T upon 100. The instrument used for the measurement of the amount of rotation in degrees caused by an optically active substance to the plane of polarized light is called polarimeter. The principle of this instrument has been already discussed. It consists essentially of two nickel prisms. One is called polarizer and other is called analyzer. Both of these are fitted in the opposite ends of the same metal tube. However, the polarizer is fixed but the analyzer can be rotated about the axis of the tube. In between the polarizer and analyzer, there is space for keeping the glass tube containing the solution. The glass is usually 5 cm, 10 cm, 20 cm, 25 cm, and the glass windows on the both ends. A circular scale is fixed on the metal tube near the analyzer, as shown in figure 5.3. Principle of a polarimeter. In the procedure, first of monochromatic light from a suitable source, usually sodium vapor lamp, it is passed through the instrument without placing the tube containing the liquid over the solution. The light emerging out of the analyzer is viewed through the eyepiece. The analyzer is rotated slowly till the field of view is completely dark. This gives the initial reading of the instrument. Now the tube containing the liquid or the solution of known concentration is placed and the shutter closed. On seeing it, the eyepiece, the field of view is no longer and found to be dark. The analyzer is rotated slowly till the field of view is completely dark again. This gives a final reading. The difference between The final reading and the initial reading give the angle of rotation alpha. It comes out to be positive, the substance is dextro-rotatory, and if negative, it's levo-rotatory. Modern instruments have numerous improvements over the simple type. However, the basic principle remains the same. Now 5.2.3 Optical activity and chemical constitution. Optical activity is a purely constitutive property that depends upon the arrangement of atoms within the molecule. It has been observed that the organic compounds which are found to be optically active contain at least one carbon to which four different atoms or groups are attached. Such a carbon atom is called asymmetric carbon atom. It is usually shown by putting a sign of star over it. A very simple example of such compound is that of lactic acid as represented below. CH3, HCOH, COOH. It is found that such compound exists in two forms, one of which rotates the plane of polarized light right called dextrorotatory D form plus form, and the other which rotates the plane of polarized light to the left is called levorotatory L form या minus form. The two form which we have same constitution in each carbon. The asymmetric carbon atom is attached to the same four atoms or groups but differ in the configuration, that is arrangement of atoms or groups in space. Thus the two forms are space isomers called optical isomers. Lebel and Van 't Hoff pointed out the difference between the forms by suggesting that in case of such molecules, the asymmetric carbon atom is represented by the center of a regular tetrahedron and the four atoms or groups attached to it are presented at the corners of tetrahedron. This gives the rise to the two different spatial arrangements which were like the mirror image of each other as shown as figure 5.4 below. Spatial difference in D and L form of lactic acid. The above two configurations are different in the sense that they are not superimposable over each other. Thus the two forms are related to each other as the rigid hand is to the left hand of the same person. The above two forms may be represented in a simplified way as follows. In the first form, the arrangement from hydrogen to OH is clockwise, and in the form second, the arrangement from H to OH is anticlockwise. Hence, if one of them is dextrorotatory, the other is levorotatory. However, by mere inspection of the configuration, it is not possible to predict as to which of form is dextro or which is levo. The two forms are said to be enantiomorphous. Enantio opposite morphic form. It means they both have opposite forms. Further, if equimolar quantities of two forms are mixed together, a third form is obtained which is optically active. This is obviously due to the fact that the rotation is caused by one form to the light is nullified or compensated by the equal rotation caused by the second form to the left. This process is called external compensation, and the substance that sustains is called racemic mixture. This can be separated into D and L form by suitable method. In case of compounds containing two asymmetric carbon atoms, example tartaric acid, a fourth atom fourth form also found to exist. In this form, the rotation caused by half of the molecule is compensated by the other half within the molecule as shown in the figure 5.54 tartaric acid. This form, which is optically inactive due to internal compensation, is called mesoform. Lastly, it may be mentioned that the optical activity is found not only in the organic compound containing an asymmetric carbon atom but also in the compounds which contain other symmetric atoms like nitrogen, sulfur, silicon, cobalt, tin, etc. Further, some compounds may not contain asymmetric carbon but are optically active because the molecule as a whole is asymmetric. Thus, it may be concluded that the optical activity is a property related with asymmetry of the molecules, and the optical activity can be used to test the presence of asymmetry in the molecule. Now we take an example 1. A solution of a certain optically active substances in water containing 1.56 gram in 100 ml rotated polarized light 4.9 angstrom in polarimeter and which has a cell 20 cm long. The D line of sodium was used as light source. Calculate the specific rotation. Now C is equals to 1.56 gram upon 100 ml. Alpha is equal to 419 4.91 degree. L is equal to 20 centimeter, which is equals to 2 decimeter. Now 100 into alpha upon L into C is equals to 157.37. Now we have another example, example 2. The value of alpha D24 lactose is 55.4 degree. What is the concentration in gram per liter of a solution of lactose which gives a rotation of 7.24 degree in 10 centimeter cell at 20 degree with sodium dilite? Alpha D20 55.4 degree, alpha is equal to 7.24 degree, L is equal to 10 centimeter, which is equals to 1 decimeter. Putting the values in the formula, alpha T 100 into alpha upon L into C. C is equals to 100 into alpha lambda T into 100 into 7.24 upon 55.4 into 1, 13.07 gram per 100 ml is equal to 137.7 gram per liter. Example 3. When alpha D glucose alpha D20 which is equals to plus 112.2 degree is dissolved in water, the optical rotation decreases as beta D glucose is formed until at equilibrium. Alpha D20 plus 52.7 is expected when beta D glucose alpha D20 plus 18.7 degrees is dissolved in water, the optical rotation increases until alpha D20 plus 52.7 is obtained. Calculate the percentage of beta foam in the equilibrium mixture. Solution. Suppose X is a fraction of D glucose in the beta form, then the fraction of alpha is equals to 1 minus x plus 1 18.7 plus 1 minus x plus 1.2 is equals to 52.7 as the x is equals to 0.636 which is equal to 63.6 which is beta, and 1 minus x is equal to 0.634 36.4% alpha. Now here are some problems for your practice you may do, and I oral it. Calculate the specific rotation of substance with a solution which contains 5 gram of the substance dissolved in 25 ml of the water and shows the rotation of 5% when introduced in 20 cm long polarimeter tube, and its answer is 12.5 degree. As 13% aqueous solution of maltose shows a rotation of 17 degree in 10 cm tube, 4D line of sodium at 25 degrees Celsius. Another solution of maltose under identical condition have a rotation of 35 degree. Calculate the strength of this maltose solution in gram per liter. When alpha D mannose is dissolved in water, the optical rotation decreases as beta D mannose is formed until an equilibrium as expected. Beta D glucose is alpha D20 minus 17 degree is dissolved in water, the optical rotation increases. Alpha D20 plus 14.2 degrees obtained. Calculate the percentage of alpha foam in the equilibrium mixture. Dipole moment. General introduction. Polar and non-polar covalent bond. A covalent bond is formed by the mutual sharing of electrons between two atoms. If the two atoms are identical, example in H2, Cl2, etc., the shared pair of electrons is attracted equally by both the atoms, and there it remains exactly in the center of two atoms as shown exactly in the center in the case of H2 and Cl2. Thus, neither of two atoms in such molecules acquire positive or negative charge. The bonds thus formed in between two identical atoms is called non-polar covalent bond. On the other hand, if the two atoms are dissimilar, example in HCl molecule, chlorine atom is more electronegative than hydrogen atom, hence the electron pair is more attracted towards the chlorine atom than towards the hydrogen atom. In other words, the sharing pairing of electron is more displaced toward the chlorine atom than the hydrogen atom. As a result, chlorine end of the molecule acquire a slightly negative charge delta negative, while the hydrogen end of the molecule acquires slightly positive charge delta positive. The bond thus formed between the dissimilar atoms have slightly different electronegativities is called polar covalent bond, and the molecule is called dipole because it had developed positive and negative poles. The situation in HCl may be represented as shown as figure 5.6. Dipole moment of diatomic molecule. The extent of polarity or polarization of a molecule is expressed in the terms of dipole moment, which is defined as follows. The dipole moment of a polar diatomic molecule is the product of the charge on the end of the molecule and the average distance between the center of their nuclei, that is bond length. In general, for a polar diatomic molecule AB in which atom B is more electronegative than A, if plus Q charge on the end A and minus Q on the B of molecule D is the average distance between the center of the nuclei. Then the dipole moment of the molecule AB is given by mu is equal to Q into D. Obviously, if the molecule is non-polar, Q is equal to 0 and hence mu is equal to 0. Third, units of dipole moment. The charge present on the end of a molecule is usually of the order of 10 raised to power minus 10 ESU, and the distance between the atoms, that is bond length, is usually of the order 10 is to power minus 8 centimeter un. Therefore, mu must be of the order 10 is to power minus 10 into 10 is to power minus 8 is equals to 10 is to power minus 18 ESU centimeter. The value is called 1 dy after the name of point work of the field. Thus 1 dy is equal to 10 is to power minus 18 ESU centimeter. Fourth, vector nature of the dipole moment. The dipole moment is a vector quantity that it has both magnitude as well direction. It is therefore represented by an arrow pointing from positive end to the negative end of the molecule. Dipole moment of a polyatomic molecule. In every polyatomic molecule containing more than two atoms, every two bonded atoms have their dipole moment. This is called bond moment. The net dipole moment of the polyatomic molecule is the resultant of the different bond moments. Obviously, the resultant will depend upon the direction of the bonds. If the molecule AB2 contains two AB bonds at an angle theta and mu AB is the value of the each bond moment, then the dipole moment of the molecule will be mu is equal to 2 mu AB cos theta star upon 2. As you know, as mu is known from experiment, there knowing the values of theta, the method is usually for the calculation of bond moment. Alternatively, knowing the value of mu and mu AB, the method can be used for the calculation of theta and hence for predicting the shape of molecule, as discussed later in the section 5.33. The experimentally observed values of dipole moment of some common molecules and the calculated value of the bond moments of some common bonds and are given in the table. H2Cl2 Br2 I2 N2 0, CO2 CS2 SnCl4 SnI for 0, HCl 1.03, HBr 0.78, HI 0.38, H2 1.84, NH3 1.46, H2S 1.10, SO2 1.63, N2O 0.17, CO 0.12, PH3 0.55, PCl3 0.78, HCN 2.93, CH4 C2H6 C2H4 C2H2 0, CCl4 CBr4 0, C3Cl 1.86, CH3Br 1.80, C2H5Br 2.03, CH3OH 1.78, C2H5OH 1.85, CH3NH2 1.24, CH3COOH 1.74. Now aromatic: chlorobenzene 1.73, bromobenzene 1.71, iodobenzene 1.20, nitrobenzene 4.23, aniline 1.56, phenol 1.70, p-dichlorobenzene, m-dichlorobenzene and o-dichlorobenzene are as 0, 1.72, 2.50. Table 5.2. Bond Hc 0.2, Hn 1.5, HO 1.6, HF 2.0, HB 0.55, HS 0.8, HCl 1.03. These are fixed arbitrarily. The result dipole moment of the groups like NO2, NH2, CH3, etc. also have been reported. These are called group moments. The value depend upon whether the group is attached to an alkyl radical or an aryl radical. The value of few groups are given below: NO2, CN, CH3, NH2. Group moment in alkyl X, aryl X, minus 3.05, minus 3.46, plus minus 0, plus 1.23, minus 3.93, minus 3.99, 0.45, 1.55. Electrical polarization of molecule. Every molecule is made up of positively charged nuclei and negatively charged electron cloud, as shown in figure 5.9a. The center of positively charge coincides with the center of negative charge. Hence, when such a molecule is introduced between the two plates of an electric field, the positively charged nuclei, and hence the center of the positive charge is attracted towards the negative plate, whereas the negatively charged electron cloud is attracted toward the positive plate of the electric field. As a result, the molecule gets distorted, as shown in figure 5.9b. This is called polarization of the molecule, and the distorted molecule with positive and negative end is called electric dipole or dielectric. The molecule remain polarized so long as the electric field is supplied between goes back to the original state as shown in figure. The electric field is switched off. That's why the type of polarization is called induced polarization. An electric dipole formed called induced dipole, since after every polarization the molecule is neutral as a whole, and this means that the positive charge at the one end must be equal to the negative charge on the other. Supposed to charge q, if it is the distance separation between the charge, the dipole moment is induced dipole, called the induced dipole moment, represented by mu I, will be given by mu1 is equal to q cross t. Evidently, the value of mu1 will depend upon the nature of the molecule and the strength of the electric field. Say x, we write mu1 is equal to alpha into x, where alpha constant and is called the probability of the given molecule. Alpha is further found to be related to the dielectric constant of the medium present between the plates, the molecule being studied according to the equation by Celsius and Mosotti. D minus 1 upon d plus 2 m upon rho is equal to 4 by 3 pi n alpha, where m molecular mass molecules, P is the density of molecule, N is Avogadro number. Celsius-Mosotti equation. Suppose an electric field applied to the two plates so that they get charged. Suppose the strength of uniform electric field produced between them is equal to E naught. If if a non-polar medium is placed between the plates, the strength of the electric field will be reduced to E, because the induced dipole called dielectrics act as in opposite direction to the applied field and hence partially neutralize the charge of the plate. As shown, the ratio E naught by is equal to dielectric constant D of or relative permittivity of the medium. From electrostatics, it can be shown that E naught is equal to E plus 4 pi I, where E is the induced dipole moment per unit volume. I is equal to mu I into N. Mu I is induced dipole moment in a single molecule, and N is the number of molecules per gram. Dividing both sides of equation 4 by E and putting E naught by is equal to D, we get D is equal to 1 plus 4 by E by E, or D minus E is equal to 4 by the intensity of the electric field strength x dependent upon the molecule is calculated by supposing that a charge unit is enclosed in a small spherical cavity which is enlarged as large compared with the size of molecule, but in comparison with the distance between the electric intensity x is made up of following parts: the field strength of charges of the plate, the charge induced on the surface of dielectric, and the constant with the charge induced on the surface of spherical cavity, plus 4.3 pi I. X is equal to E naught plus 4 by 3 pi I minus 4 pi I. Substituting the values of E naught from equation 4, we get X is equal to E plus 4 pi I plus 4 by 3 pi I minus 4 pi I E plus 4 by 3 pi I. Substituting the values for pi I from the equation 5, because X is equal to E plus D minus 1 by 3 E, 1 plus D minus 1 by 3 E, D plus 2 by 3 E. From equation 7, at E plus 4 by 3 pi I is equal to D plus 2 by 3 into E D plus 2 by 3 minus E into E is equal to 4 by 3 pi I. D minus 1 by 3 into E is equal to 4 by 3 pi I is equal to mu I into N, alpha into X into N, alpha into D plus 2 by 3 into E into N. Equation 9 become D minus 1 by 3 into E is equal to 4 by 3 pi alpha D by D plus 2 by 3 E into N, D minus 1 D plus 2 4 by 3 pi N. Or if P is the density of the substance placed between the charged plates, if I of the medium between the charged plates, and M is the molecular mass, then the molar volume of the substance M by V. If N represents Avogadro number and the number of molecules per unit volume is I, N is equal to N upon M by P, and P upon M. Substituting the values in equation 10, we get D minus 1 upon D plus 2 is equal to 4 by 3 pi np upon m into alpha d minus 1 d pi to mip is equal to 4 by 3 pi ne. As all quantities on the right hand side of equation 12 are constant, alpha being constant for a given substance independent of temperature, therefore the quantity on the left hand side of the equation 12 must also be constant independent of temperature, and depending upon the values of nature of molecules, the quantity is called molar polarization, represented by further it is applied field produced and induced in the molecule, relative displacement or distortion of the electrons and nuclei. P often called induced or distortion polarization and is represented by pi or pd. Thus pi pd is equal to d minus 1 upon d plus 2 upon m. Induced molar polarization defined as the amount of polarization produced in 1 mole of the substance when placed between the plates of an electric field of a unit. And from equation 113, it is evident that the unit of pi will be same as those of m upon p molar volume. Hence p is usually expressed in centimeter cube per mole. Expression 13, given the relationship between the electric constant and the porosity of was first derived by Mosotti in Celsius and called Mosotti-Celsius equation. Effect of temperature on polarization. Using equation 13, the values of molar polarization have been determined for a few number of substances. It is found that whereas molar polarization of number of substances such as O2, CO2, and 20CH4 are constant and independent of temperature, the polarization value for some other substances such as HCl, CH3Cl2, CaCl3, C6H5, and O2CH3Cl do not come out to be constant but decrease with increase in temperature. The observation has been on the basis of measurement of dipole moment in the study of molecular structure as explained below. In the case of molecules such as HCl, CH3Cl, the center of the positive or negative charge do not coincide with each other. They thus possess some dipole moment even in the absence of electric field. A dipole moment thus possessed by the molecule is called permanent dipole. In the absence of the electric field, these permanent dipoles are oriented in a random manner due to the thermal agitation as shown in figure 5.11. However, in the presence of an electric field, two disturbing effects take place. These are the electric field will tend to rotate or reorient these dipoles in the direction of the electric field will tend to polarize the molecules. If the molecules were stationary, the dipole would have been oriented perfectly parallel to the electric field that are the right angles to the plates of the electric field. Method of measurement of dipole moment as explained above. The basic equation for the determination of dipole moment is equal to Pd minus 1 upon d plus 2 upon a plus b by t, where a and b constant, b is equal to 4 pi n mu square upon 9. The experiment involves the determination of the electric constant and the density p at the different temperature t. The values p and calculated and plotted against 1 by t. Pt is found to vary linearly with 1 upon t. Substance possesses a permanent dipole moment and the value of the dipole moment is calculated from the slope of line. On the other hand, if P is found to be independent of temperature and the substance do not permanent dipole moment, it is non-polar. The dielectric constant required in the above equation is determined by first measuring the capacity of a condenser in vacuum between place C0 and the measuring the capacity of the same condenser when filled in the given substance. The dielectric constant of the substance is then given by this equal to C upon C0 refraction method according to the Clausius-Mossetti equation. The induced or distortion molar polarization PiPd of the molecule is caused by PiPd d minus 1 upon d plus 2m into m upon b is equal to 4 by 3 pi n. As d diagonal is a pure molar polarization P simply molar volume of the matter. Further, it is all independent of the temperature of the substance, is non-polar and do not have permanent dipole moment. For such molecules, it was derived by J.C. Maxwell that the dielectric constant of substance is related to its refractive index for a long wavelength according to the equation d is equal to n into infinity square. Substituting the values in equation above, we get Pd is equal to n into infinity square minus 1 upon n into square plus 2m upon p 4 by 3 pi n alpha. However, an infinity square cannot be defined by extrapolation of infinite wavelength of the values of radioactive indices measured with visible light. This is because visible light can be displace only electrons, whereas the positively charged may be unaffected. This is the distortion. Polarization can be considered to be sum of the electrons polarization and the atom polarization. To find the value PV is equal to is necessary to measure the refractiveness in using infrared rays because they displace the heavy atomic nuclei as well electron, but measurement of the refractive index with infrared radiation is difficult. Hence, the problem is solved by finding the electron polarization by measuring the refractive index using visible light dip n square minus n plus 2 n company as an approximation. 5% of the value is added to account for P to get the total value. Pd is equal to P minus P 5.5 EP. And then, as before, total polarization of a molecule possessing a permanent dipole moment is the sum of two terms. The first called distortion polarization P and the second called orientation polarization due to permanent moment possessed by the molecule. Hence, we can repeat is equal to Pd plus P naught. Putting the value P naught by dy equation with P naught is equal to 4 by 3 pi n p square upon 3 k. Taking example 5, Pt is equal to Pd plus 4 by 3 pi n mu square upon 3 k. Putting the values constant, simply we get mu is equal to 0. Pt can be determined by finding the dielectric temperature at Pd and cannot be used in radiation by approximation method. This method is simplified only at one temperature. Dilute solution method equation using gases and vapors only for substances which are not gases or cannot be converted into vapors. The following procedure is followed. Dilute solution method equation 20 is applicable to the gases of weapon only. For substances which are not gases cannot be converted into vapors. The following procedure is followed. We dilute solution of the given substances prepared as in a non-polar solvent such as benzene, carbon tetrachloride, CS2, etc. The density of the dielectric constant of the solution are determined at various temperatures. At each temperature, the molar polarization of the solution P5 is calculated using the relation when x1 x2 mole fraction of the solvent in the solution M1 M2 are the respective molecular mass and P. The density of the solution if molar polarization of the solution is related to the polar polarization of the solvent and x1 and x of the solute as P5 is equal to PS is equal to x1 P1 x2 P2. Thus the values of x1 x2 P1 P2 and molar polarization of the solute can be calculated. The value of Pt obtained at different temperatures is plotted against one upon t, and the value of mu is then calculated from the slope of line as explained earlier. Dipole moment and chemical constitution. The knowledge of the dipole moment of a molecule can be applied in a number of ways to study chemical constitution. A few important applications of dipole moment are briefly described below. In compared relative polarity of molecule, for example, dipole moment of HF, HCl, HBr, HA 2.0, 1.03, 0.78 and 0.3 divide respectively. This shows that the polar character of the HF molecule decreases as well as from HF to HA. In calculating percentage ionic character of a polar covalent bond, for example, the dipole moment of HCl is in 1.03 T, and if bond were 100% ionic, the each covalent and would acquire full 1 unit charge. The bond distance in HCl is taken to be this. Hence, if HCl were 100%, the dipole moment would have been taken 4.8 into 10 to 1 Actual value of dipole moment of HCl 1.03 diopter 1 percentage of ionic character of HCl bond 1.03 6.11 into 100%. In predicting the geometric shape of the molecule, the fact that the dipole moment is a vector quantity and a particular bond has almost a constant value of bond moment is useful in predicting the shape of the molecules. A few cases described below. Diatomic molecule, triatomic molecule. Diatomic molecule is always a linear irrespective of its dipole moment. Triatomic molecule. In triatomic molecule, the value of the type AB2, these are two possibilities. The dipole moment of the molecule may be 0 in case of CO2 and CO2. This shows that these molecule one bond is equally opposite and the other, hence the molecule must be linear as shown. The molecule may have different value of the dipole moment. Obviously, in the cases the possibility of linear shape is ruled out, the two bonds must have a definite angle between them, and which can be calculated if we know the bond moment as discussed in section 5.3. For example, the bond moment hydrogen is 1.6 d and the bond angle is calculated to be nearly 1.105. Thus, H may be represented as shown in the figure. Such molecule are called pentamolecule and the shape is called V shape. Tetratomic molecules. In tetraatomic molecules, the type F with the two simple possibilities are the dipole moment of molecule may be 0. In such case, all the four atoms must be in one place and the angle between the bond must be equal in BF3 and shown in figure 1.5, such as shape. The dipole moment of the molecule may be in such case all the four atoms must be plane and the angle between the bond must be equal in BF3 as shown in figure 5.15, such as shape called planar trigonal. The molecule may have some definite value of dipole, example NH3PF3. This indicates that the one atom lie out of plane of the rest. For example, molecule NH3 may be represented as such as a shape is called pyramidal geometry. Pentatomic molecules. A pentaatomic molecule of the type AB4 which commonly come across are CH4, CCl4, SiCl4, SnCl. The dipole moment of this molecule may be found to be 0. This is possible only if the molecules have symmetrical or regular shape. regular geometry so that the different bond movement cancel each other. The experimental fact that confirm these molecules have tetravalent shapes are represented below. The differentiating the systems isomers. So the systems isomers are represented at HCX, HCXC, C double bond, CHX, HXCH. It is clear that the transform will be non-polar. I will have zero dipole moment, whereas cis form will be polar. will have definite dipole moment. For example, in case C dichloroethylene putting XC cis form, it has been found a dipole moment of 1.5d, while this transform found to have zero dipole moment. Differentiating the 0 m and p isomers as benzene is a regular hexagon and dipole moment is 0. Therefore, substituting rotating groups into the ortho, meta, and para position, the distributing derivatives will have different dipole moment of the ortho, meta, and para isomers as shown in figure below. Obviously, para will have zero dipole moment and meta will have less dipole moment than ortho. In supporting the possibility of resonating structure, for example, nitrous oxide molecule N2 has a small value of the dipole moment 0.1. If the molecule is supposed to have any one of the following two structures, in the dipole moment should be high. This compound molecule is a resonance hybrid structure of first and second. Numerical problems on dipole moment. A recapitulation of formulas and unity. Mu is equal to q cross t, where is mu is equal to dipole moment in ESU centimeter, which is device q charge, in ESU, which is the very small unit of charge, is equal to intermolecular distance or bond distance in centimeter. Percentage ionic character observed dipole moment upon calculate dipole moment taking bond found to be 100% ionic into 100. Example 1. The bond length of hydrogen is 1.60 angstrom and found to have a correct value for its dipole moment by units if represented in the complex ionic form of charge on the electron. Is this solution for HI? We have given that d is equal to 1.60 angstrom, 1.60 10 is to power minus 8 centimeter. Q is equal to 4.8 into 10 is to power minus 10 ESU. Mu is equal to Q cross T, 4.8 into 10 is to power minus 2 is 1.60 into 10 is to power minus 8, 7.68 into 7.68 T. Magnetic susceptibility. General introduction to some terms used. Magnetic permeability. If two magnetic balls of strength m1 and m2 are separated by a distance r, then the force acting between the force is equal to 1 by mu m1 into m2 upon r squared. The quantity mu is used in the above expression is called the magnetic susceptibility of the medium between two poles. It is defined as the relative tendency of the magnetic line of force to pass through the medium as compared to that of the vacuum. For vacuum, mu is taken as equal to 1. Similarly, for air, mu is taken approximately q equal to 1. Diamagnetic, paramagnetic substance as mentioned above. For vacuum, mu is equal to 1. Other medium, mu can be less or greater 1. If mu is less on the magnetic line of all force prefer to pass through the vacuum rather than angle the substance comprising the medium. In the other words, the magnetic lines of force are repelled away from the substances such as said to be diamagnetic. On the other hand, if mu is greater then the magnetic line of force have greater tendency to pass through the substance other than the vacuum. In other words, the magnetic line of force are attracted towards the such substance are called paramagnetism. If mu is very high and on the other hand trend is to pass through more, the tendency of the substance to attract the magnetic lines of force very high and the substance is said to be ferromagnetic. Ferromagnetism is exhibited by mainly by iron, cobalt, nickel alloys. It is a property of greater interest in the subject of physics only chemistry. In chemistry, we only deal with diamagnetism and paramagnetism. The behavior of diamagnetic and paramagnetic substances in a magnetic field is shown diagrammatically. Now, third, magnetic susceptibility. As seen above, if any material is placed in the magnetic field, the strength of the magnetic field in the material is different from that in the vacuum. The strength of the magnetic field thus present in the material called magnetic induction. If hydrogen is the strength applied to the magnetic field and B is the magnetic induction in the given material, the two related according to the equation B is equal to H plus 4 pi L. I represent magnetic moment per unit volume And the material called intensity of magnetization, it is maybe positive, negative, depending upon whether the material is paramagnetic or diamagnetic, or the intensity of magnetization produced per unit length of light magnetic field called specific magnetic susceptibility. It is usually represented by uh, chi psi. Thus mathematically psi is equal to I upon the quantity is usually measured experimentally in the study of magnetic properties of different metal multiplying the specific magnetic susceptibility with the molar volume of the material we get. What is the magnetic susceptibility per mole per magnetic susceptibility is used represented by psi. Mathematically, the molar magnetic susceptibility may be defined as the intensity of magnetization induced per mole of the material by the unit field strength. Quite often, it is conveniently to deal with the quantity xm in the place of x. Further, the magnetic induction B is related to the strength of the applied magnetic field hydrogen according to the equation B is equal to mu h, which means the magnetic permeability of the medium. Also from equation I is equal to chi h. Substituting the values of P and I from the equation 4 and 5 in the equation 1, we get mu h is equal to h plus 4 pi alpha h mu is equal to 1 plus 4 pi I chi. Since in the above discussion the magnetic moment per unit volume of the material alpha is the volume susceptibility of the medium, however for most practical purpose we use susceptibility is obtained by dividing the volume susceptibility by the density of the material. Hence we have mass susceptibility xi is equal to psi by p p xi. Substituting the value in the equation we get mu is equal to 1 plus 4 pi p x psi a dash mu minus 1 1 4 pi p. This gives the relationship between specific magnetic susceptibility and the magnetic permeability of the material density. Since for diamagnetism mu is less than, therefore the specific magnetic susceptibility or negative for such a substance. On the other hand, for the paramagnetic substance mu greater, therefore x small. But for ferromagnetic substance as mu is very large, so it's very large. The magnetic susceptibility are generally determined by method putting forward by Gorey in 1889. It's shown in briefly explained below. The material under examination is taken in a thin cylinder of a tube when it is suspended vertically with a wire from one arm of the balance between the two poles of an electromagnetic, such as the lower end of the cylinder is nearly middle of the poles and the electromagnet. The cylinder is now counterbalanced in this position. By placing the weights in the other plane of the balance, the current is now switched on into the electromagnet. If the substance is paramagnetic, the cylinder will be pulled down and so that the magnetic lines of force can pass through. On the other hand, the substance right the cylinder pushed upward so that the less magnetic lines of force may pass through it. In the first case, so extra watts will have to be added in the bottom, whereas the second case, some weights will have to remove from the pen to restore the balance. Since the change in weight equal to the magnetic force acting on, since the delta m is delta mg is equal to half psi into psi e is delta h square, which is the acceleration due to gravity, and that delta mg gives the change in weight. The right hand side of the magnetic force acting on the material of the volume susceptibility psi V is the area of cross section of the specimen, H is the field strength chi e, and the volume susceptibility of the air value of psi is 0.03 into 10 to the power minus 6 using the equation 9, and value of the x can be calculated in the above calculation. The above value of the field strength H is also required. However, the necessity of measuring hydrogen H and E can be eliminated in the experiment. The first formed with substance known as susceptibility using the same magnetic field in the same magnet cylinder. For taking the substance, usually water is taken as standard substance for this purpose. Then evidently we will have delta m upon delta n x psi m minus psi a psi m minus psi e, where psi m change in mass where the sample under examination is placed in the magnetic field, and the delta mx is the change in the mass, and water is taken as the same cylinder and placed in the same magnetic field, and the x is the magnetic susceptibility volumes of the same sample. 5.4.3 Magnetic susceptibility and molecular structure. as detail of the magnetic susceptibility of large number of organic and inorganic compounds carried by Pascal during his revolved many other physical properties such as molar reflection, Pareto, the magnetic susceptibility is an additive as well as constitutive property. The value assigned to the various atoms and the structural factors bond triple bond rings can be experimentally determined. The values of large number of elements and compounds. The value of magnetic susceptibility for some of the atoms and structural groups are given below: hydrogen, carbon, oxygen, oxygen in alcohol, ether in ketone, ester, acid, nitrogen, nitrogen in open chain ring, amines, fluorine, chlorine, bromine, and their magnetic susceptibility are as follows, which is in this all we will multiply it is 10 is to power minus 6. Starts with hydrogen minus 2.13 minus 6.00 minus 4.61 plus 1.73 minus 3.36 minus 5.57 minus 4.61 1.54 minus 1.11.5 minus 2.01 minus 330.6. Structural factor: carbon double bond, nitrogen double bond, carbon nitrogen double bond, carbon triple bond, nitrogen carbon double bond, benzene ring. And their magnetic susceptibility minus 5.4 1.9 8.2 0.8 minus minus 0 minus 1.5. The calculation of molar magnetic susceptibility of a compound for an aromatic and structural values help to decide between the all alternate structure for a compound. To confirm the structure of the compound by comparing the calculated value with the experimental value, and few examples are illustrated below. Diamagnetic substance was studied for this purpose because their magnetic susceptibility is independent of the temperature and nearly same as substance in the gaseous. Example: confirm the structure of benzoic acid. The magnetic susceptibility contributes to the various atom and structure factor, and hence its values as xm can be calculated as total observed value. Total observed value as a value is very close to the observed value. The given structure is correct. Explanation of diamagnetism and paramagnetism. Electron in an atom have orbital motion as well as spin motion. As they are charged particles, their motion produces a small magnetic field. If all the electrons in a molecule are paired, then the magnetic moment of the electron spinning in one direction is cancelled by the magnetic moment of the other electron spinning in opposite direction. Then the net result is and that is substance has zero magnetic moment. In such a space we have magnetic fields are induced by substance and the opposition of the external. As a result, the substance is repelled in the magnetic field. This type of behavior is observed for the diamagnetic substance. The diamagnetism is exhibited by those substances which contain paired electron only, no unpaired electron present. On the other hand, if a substance contains some unpaired electron, the magnetic moments electron do not cancel out completely, hence the substance permanent magnetic moment of its own. In fact, each unpaired electron behave like a micromagnet with a definite magnetic moment. If such a substance is placed in external magnetic field, and the micromagnets will arrange themselves parallel to the external field, and the induced magnetic field is insufficient to overcome the permanent magnetic moment of the substance. The substance are therefore attracted in the magnetic field instead of being is exhibited those only substance which carry unpaired. Determination of magnetic moment of a paramagnetic substance. As explained in each atom ion molecule, paramagnetic substance behave like a micromagnet which define inherent magnetic moment of magnitude where such as substance is placed in the external magnetic field. The micromagnets arrange themselves parallel to the applied field. However, the tendency is opposed to the thermal motion of the particles. Susceptibility of paramagnetic substance vary करती with temperature, hence the actual arrangement taken will depend upon the temperature. Langevin in 9.1905 put forward the following relationship between molar magnetic susceptibility and magnetic moment mu m and temperature T. Xm is equals to alpha m into mu square m n upon 3 k, when n Avogadro number, k Boltzmann constant, alpha m constant for the given. It is represented the diamagnetic molar susceptibility of the substance induced by the applied magnetic field. In equation 11, all the quantities are constant except xm and xt. Thus determine the xm for the given substance and the different temperature density. Plotting x and versus 1 upon n straight line graph will be plotted. The slope of the which may be equal to mu square m upon n upon 3, and mu can be calculated. The units m and arg goes inverse. However, it is usually expressed in terms of Bohr magnetons Bm, relationship between magnetic moment and the number of unpaired electrons. The total magnetic moment of an atom and ion molecule, the sum of the two following values in magnetic moment to orbital motion of the electron, it is equal to L into L plus 1 Bohr magneton, where L is azimuthal or orbital quantum number for that electron. Magnetic moment due to spin motion of the electron is equals to S into S plus 1 Bohr magneton, whereas is the quantum number having value equal to 1 upon 2. If the ion molecule are considered in a state of free atoms, it is expected that the orbital motion of the electrons are tied into the nuclear configuration of the molecule or so tightly that they are unable to line with the applied magnet. Hence, the magnetic moment contribution due to the orbital motion is negligible. Thus, the magnetic moment of the molecule or the ion is mainly due to the spin motion of the electrons, hence is called spin magnetic moment. Thus, we have m is equal to 2 on root s into s plus 1 Bohr magneton. S is the spin quantum number for the unpaired electron for a molecule ion containing a number of unpaired electrons. The expression is m is equal to s plus 1. S is s spin quantum number. Thus for unpaired electron, s is equal to 1 by 2. For 2, s 2 by 2. For 3, s 3 by 2, and so on. For general and unpaired electrons, s is equal to n by 2. 13 becomes mu is equal to 1 root n by 2, n by 2 plus 1. Mu is equal to 1 root n plus 2 Bohr magneton. Relationship between molar magnetic susceptibility and the number of unpaired, taking alpha m to negligible in equation, is dependent on the diamagnetic molar susceptibility of the substance induced by the applied magnetic field. Equation 11 becomes L psi m is equal to mu m square upon 3 kt. Substituting the values of mu m from this, x m is equal to n upon 3 kt and n plus 2. Application of magnetic susceptibility in confirming the structure of given molecule, in calculation of the number of unpaired electron in a molecule or ion, and knowing the molar magnetic susceptibility, which can be determined experimentally. The number of unpaired electron present in a molecule or ion can be calculated using equation. This helps understanding the electronic structure for a number of molecules. For example, the magnetic susceptibility of oxygen found to be 3, 4, 0, 0, and 10 is to 1, which is shown that it contains don't pedal. Thus, the structure of oxygen molecule should be represented in the study of coordination compounds. The main application of magnetic is in the study of chemistry coordination compound of transition element. Measurement of the magnetic state help to know the number of unpaired electrons in the complex, help and correct assign to the complex sign. In some cases, in the magnetic susceptibility values of the complex FEC in 6 is minus FEC F6 in same coordination number, such as that there is non-paired electron present in the former, whereas there are 5 unpaired electrons present. Later there are explanation in establishing the formula certain compound. For example, in establishing formula certain compound, for example, shown with the formula hydrophosphoric acid H4P2O6. In explaining the existence of odd electron molecules, a compound containing odd electrons are expected to be paramagnetic, but actually found to be fugacious compound, namely nitric oxide, nitrogen dioxide, and chlorine dioxide. In explaining the formation of free radicals, some highly substituted aromatic compound have a tendency to form into this fragment called free radicals. Dielectric property of solid insulator do not conduct electricity because of the electrons present in them are lightly tied. Individual atom or ions do not free to move. However, when electric field is applied, polarization takes place because nuclei are right at one side of the electron cloud. To the other side, the dipole are formed. In addition to this, these may be permanent dipole in the crystal. These dipoles may be aligned through themselves in a manner so that the crystal have a net dipole moment, piezoelectricity, and pressure electricity. When mechanical stress is applied in such crystals so as to deform the electricity produced due to displacement of ion, the electricity thus is called piezoelectricity, and the crystal is called piezoelectric crystal. Conversely, if the electric field applied to such crystal, atomic displacement takes place resulting into mechanical strain. Thus, such crystal act as a mechanical electrical transducer. As for example, piezoelectric crystal induce titanium, barium, lead, lead zirconate, PbZrO3, ammonium dihydrogen phosphate, NH4, H2PO4, and quartz. These crystals are used as pickups in the record player, whereas they produce an electric signal by application of pressure. They also used in microphones, ultrasonic generator, sonar detector, pyroelectricity, ferroelectricity, and ferroelectricity. Some piezo crystals, when heated, produce small amount of electric current. The electricity produced is called pyroelectricity. Pyro means heat. In some piezo crystals, the dipole are permanently polarized, and even in the absence of electric field, however, apply electric field, the direction of polarization changes. The phenomena is called ferroelectricity due to the analogy with ferromagnetism. Examples of ferroelectric solids are barium stannate, BaTiO3, sodium potassium tartrate, Rauchelli salt, and cold potassium dihydrogen phosphate is found to their ferromagnet salts are piezo, but they are not reverse in true. Antiferroelectricity. In some crystals, the dipole align themselves in such a way that the alternating they point up, they down. The crystal do not possess an innate dipole moment. Such crystals are said to be antiferroelectric. A typical example of such crystal is lead zirconate. Uses above properties of solids. The various properties of the solids and as explained and used in electronic and magnetic devices such as transistors, computers, and telephones, etc. Thank you.